Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 14 in the series on section 3.2, Determinants. Although we won't be able to give a complete characterization of the question, what is the determinant, we can say that a determinant is going to be a number that we can assign to a n by n matrix. Knowing whether or not this number is non-zero tells us something about the matrix and about systems of equations. We're going to see presently how we can assign a matrix to a system of equations, and if the determinant of that assigned matrix is non-zero, then this system of n equations and n unknowns will have exactly one solution. This is going to go hand in hand with finding out if a matrix has an inverse matrix, that is to say, another matrix with whom its product is the identity matrix. And there are other very interesting geometric facts that go along with the determinant related to the change in volumes of certain shapes. We won't really have time to go into that, although you will see it perhaps in Calc 3. I would suggest, if you're interested, taking a course in linear algebra. So how do we get this number called the determinant? We're going to look at the recursive definition for the determinant, but for now, let's just say we can calculate the 1 by 1, 2 by 2, and 3 by 3 determinants with the following formula. The determinant of a 1 by 1 matrix is just its sole entry. The determinant of a 2 by 2 matrix takes the diagonal product AD and subtracts the diagonal product CB. And the determinant of the 3 by 3 matrix can be found in several ways. One of them is to take the numbers along the top row, A, B, and C, and multiply by this term that looks a little bit like the determinant we looked at for a 2 by 2, with this negative sign here attached to the B. So let's break that down. We have A times the determinant of this little submatrix EFHI, then minus B times the determinant of this kind of submatrix DI minus GF, and then plus C, which is here, times the determinant of this submatrix DEGH. So we will look at how that pattern generalizes, but this is one way that you can quickly calculate the determinant of a 3 by 3 matrix. To give some kind of formula for the determinant, we'll need to first talk about the minor of a matrix. The minor is going to be the determinant we get when we delete a certain entry. So we would say, for example, the minor associated to 1, 3 is what would happen if we took the row 1, column 3 entry, which is a 4, deleted it along with the rest of row 1 and column 3, and took the determinant of that submatrix, which would give me a 2 in this case. Now, we are going to assign pluses or minuses to that minor depending on the value of this term, -1 to the I plus j, where we're looking at indices I and j for the location of our entry. This term is called the cofactor. So this would be a minor, but possibly with a negative or positive 1 up here. For example, if I was given the following matrix, how would I find the cofactor of 2, 2? Well, I would delete second row, second column, and get the following submatrix. This has the minor 5. Then we would take 2 and 2 and plug it into this exponent to give me positive 1, which tells me the cofactor is also 5. Finally, we can look at the formula for the determinant of an m by n matrix. That's going to involve the following expanded sum. We could take any row, for example here, this is row j, and then multiply every entry in row j by the corresponding cofactor, and then sum these all up over the columns 1 to n. Now, actually, we could do this for columns as well. We just need to expand down the entries of a column and multiply by its cofactors. And there are other more general formulas for the determinant as well. This kind of freedom of what we can choose for a row or a column to expand along here should let you know that there's more going on with the determinant. But for right now, we'll just use expansion along rows times cofactors for the problems in this assignment. To get the formula for the inverse of a matrix, we're going to need to talk about the transpose of one. The transpose is just what you get when you switch the rows and columns of a matrix. For a square matrix, that's going to look like flipping around the diagonal. So holding the diagonal entry fixed and then flipping those entries, like here 6 goes to 4 and 4 goes to 6, that are the off-diagonal entries. Now, if we have a square matrix, an n by n matrix, we can make a cofactor matrix by putting the cofactors in for each entry. This would be the determinant of the matrix we would get if we deleted this row and column times the appropriate positive or negative 1. Now, once we create such a cofactor matrix, we're not far off from finding the inverse. As long as the determinant isn't 0, then the inverse is the transpose of the cofactor matrix divided by the determinant. So we would scale or multiply every entry by 1 over the determinant of A. And you can see here from this formula that we would have a serious problem if the determinant was 0, because that would be an undefined term. In fact, if the determinant is 0, then A does not have an inverse, and we would call A a singular matrix. Let's calculate the determinant of this matrix A here, first by formula, where we would take the diagonal entry, -3 times -5, subtract from that -5 times 3, which would give me 15, plus 15, which is 30. We should also look at how to put such an entry into the calculator. Let's go to second matrix. Here we have a list of some matrices I've already stored. Going over to edit, let's change the dimension of this matrix to a 2 by 2 matrix and put this in as -3, 3, -5, -5. Once we've put these entries in, this is now what the calculator will have in its mind when I say matrix A. So going back to second matrix over to math, the first entry is det, for determinant. So now we're going to go back into the names of matrices and put matrix A right there, and it will tell us the determinant. For the next one, even by formula, we can see if these two rows and columns match here, if we have two copies, then we're going to wind up with a 0 when I take the determinant. Now, that's actually a more general fact that we'll address later. If any two rows repeat, the determinant will be 0. Now, we can't always plug it into the calculator because sometimes our entries are unknown quantities. In this case, we need to expand by using the formula in order to get the following quadratic equation. That quadratic equation can be solved by factoring to give me the following two entries. Question 4 asks for the cofactor 1, 2. So we delete the first row, second column to get the following minor. Now this minor turns out to be 0 because we have repeated rows. That means that the cofactor is also going to be 0, but we should get into the habit of plugging in these two numbers, 1 and 2, into the exponent of -1. That's an odd, so this is a -1, and that means we get 0 overall when we multiply it out. Here we have a more interesting cofactor question, and I'd like to use this as an opportunity to introduce another way of calculating the 3 by 3 determinant. This is a special case formula for the 3 by 3 called Leibniz's rule. Now, if I look at deleting the first row, second column, I get the following submatrix: 1, -2, 7, 4, -1, -1, 8, 6, 8. What we can do is take two copies of the first two columns and put them next to our matrix. And this helps us see the following diagonals. The diagonals in green, we take in product, which gives us these terms. The diagonals in red, we could take in product, which gives us these terms. And we want to subtract the diagonals in red from the diagonals in green. That gives us the following value, 302. Now, the cofactor matrix here will be -1 to the power of 1 plus 2, which is an odd, and so this becomes -302. Of course, it doesn't hurt to plug our matrix values carefully into our calculator and check the determinant again by running the determinant command on matrix A. Now keep in mind that's not our cofactor, that's just our minor, but I think it takes some of the heavy lifting out of it. For number 6, they're asking us essentially about the minors for this particular matrix, expanding along the second row. So notice if I delete the second row and the first column, I can take that determinant in order to get these values. Likewise, second row, second column, I get 5, -4, -3, and 1, and to get -7. And last, delete the second row, the third column, to get 5, 5, -3, -5, which has determinant -10. Now, since we've already done all this work about expanding our minors, we could take the determinant of A pretty easily just by taking the sum of the row entries times the corresponding cofactors. So keeping in mind that I need to change my sign for my cofactors, we could expand matrix A down this row. So here I have this entry times minus 1 to the 2 plus 1 times our minor 4, 2, 1 to give me my cofactor 2, 1. And we're just going to do this down the row, going through each column to do these other entries here and here. And if we do this, we'll get 98. And plugging these entries into our matrix A, we could check our work appropriately. Moving on. Here they want us to find the determinant. There's a variety of ways we could do that. We could expand the first row or any row or column we like and expand by minors, that is to say multiply by cofactors, and we would get the following. We could take our Leibniz formula, expand it out to get the following, or we could put the entries into our calculator and calculate the following determinant accordingly. To solve the following equation involving the determinant, we need to expand the determinant in terms of its formula. Here I've used Leibniz's formula, but you could use either. But all that's required is to write down the correct products, the sums, keep your signs straight, and then group like terms and solve, and this just becomes a linear equation. So really the hard part is writing this out in terms of the determinant formula. Question 9 is a bit more conceptual. Let's see if we can discover the rules that are associated with the question in each case. Here we see that we have multiplied every element in a row by a certain constant. How does this change the determinant? Well, notice that I could rewrite this in terms of cofactors with a 4a instead of an a, and so on. That lets me factor out a 4, and so I'm really just looking at 4 times the determinant of m. In this case, that's 16. So what's the rule here? If we multiply a row by c, we need to multiply the determinant by c. On the other hand, if I multiply the entire matrix by 4, that means multiplying each entry by 4. Now, looking at Leibniz's form of the determinant, we could see that there's going to be 3 4s in each entry that we could factor out and then get the original factor of the determinant. That's going to give me 4 to the 4th, or 256, 4 to the 3rd times 4. And what do we see here for the rule? Well, every entry would have an extra c in it in this case. And since there would be n such terms in each product, we wind up with c to the n that we could factor out. So if we take the determinant of a constant times the matrix, it actually depends on what the dimension of that matrix is. An n by n matrix, we're going to pull out times c to the power of n from our determinant. Here, what we've done is switched a row with another row. We've interchanged their positions. And writing down the formula that we get, we kind of interestingly see some repeated terms. If I look at Leibniz's formula for the original one, this is really just off by a sign. All that's happened is we have changed the sign, but the actual terms haven't really changed value too much. This tells us that this is just negative the determinant of m. And in fact, that's a rule. Switching rows or switching two columns will change the sign of the determinant only. Here we have some proof, or I guess I should say some more evidence for the pattern that we saw in the first page of problems. If I have repeated rows, I'll have 0 determinant. Well, if we went to go write out expansion by minors along the bottom row, then this would be our formula for the determinant. But that would just be 0 in each case because we would have a difference of 2 like things. This means that if any 2 rows, or for that matter any 2 columns, are repeated, the determinant will be 0. That's not a necessary condition for the determinant. That is to say, there are some determinants who are 0 without repeating any rows and columns. But if we ever saw 2 repeated rows or 2 repeated columns, the determinant would be 0. Finally, what we have here looks like taking 6 and adding row 2 times 6 to row 1 and having that be our new row 1. Let's see if we can't use that idea that there's something common in each one of these entries. We've added 6 times the second row to figure out what's going on here. Well, if we expanded this along the first row by minors, we would have the following entry times the following subdeterminant, along with these following signs. Now what I'm going to do is I'm going to factor out the ones that go with the determinant of the original matrix M. That's A times EI minus H, and so on. What's left would be 6 times D times the product EI minus HF, and so on. So this actually looks like 6 times the determinant of some other matrix. What other matrix? Well, it would be this one, the one that has DEF along the top row and all the rest of the entries the same. But that's a repeated row. That means this determinant would be 0, and we don't get anything else other than the determinant of M. This leads to a rather surprising fact, that if I add a row times a constant to another row, this has no effect, 0 effect on the determinant. That's a pretty interesting fact that's going to come up later when we look at solving equations using row operations. As we discussed, the matrix being 0 tells us something about whether or not it has an inverse. Matrices which do not have an inverse are called non-invertible, or singular matrices. Let's see if we can follow along for the formula of finding the inverse of this matrix. First, we would find its determinant, which we could using the formula for a 2 by 2. Then we would find its cofactor matrix, keeping in mind to watch your signs. Remember, it's not just covering up the first row and second column here. We need to multiply that by -1 to the 1 plus 2, which gives us +2 total. So this would be our cofactor matrix, but taking its transpose, we would have the following, and then dividing 1 into each one of these terms, we would have the inverse of matrix A. There is also a calculator command for finding the inverse of a matrix. Let's first edit our list of matrices and install the correct dimensions of 2 times 2. Then let's put in our values, and once these are in place, let's quit back to the main screen. Go to second matrix to retrieve your matrix A, and the command we're going to use is actually this button here, what we usually use for the reciprocal of a number. Plugging that in will output the inverse of matrix A. Notice that if I take matrix A and multiply that by the inverse of matrix A, what I'll get is the identity matrix for 2 dimensions. Likewise, to find the inverse of this matrix, we could expand by rows to find the determinant. That's most easily done along the bottom row where there's all these zeros, because then we just have 0 times the determinant minus 0 times this determinant plus 1 times this determinant, which is 1, to give me 1 in total for my determinant of this matrix. Then we could also look at the cofactor matrix. That calculation is straightforward, right? We would cover up this element here. We would look at the 3 minus 2, 0, 1 matrix, and we would assign the appropriate sign in this upper left-hand corner. That's a positive. Then we take the transpose of that matrix, flipping it around the diagonal, and then we want to divide every entry by the determinant. If I do this, we get the following inverse for our matrix. We should also check our work using the calculator. So let's go put into a 3 by 3 matrix, putting these entries in for our entries of matrix A. We quit back to the main screen, and taking the inverse of this matrix using the -1 power button here, we get the following, and check our work against it. Now, let's see how we can use the inverse of a matrix to solve a system. The main idea I'll provide in brief over here. If I can rewrite this system as one matrix times another, and that matrix here, this column matrix, is the matrix of our variables x, y, and z, well, I could solve for all of them simultaneously just by using the inverse matrix multiplied on both sides. The inverse matrix multiplication cancels here, and on this side we have A inverse times B. Let's take a look at how this would go. We want to take our coefficients of each variable and encode them in their own matrix here. Now, multiplying by the column matrix x, y, z would give me exactly these sums and differences. And we want that to be equal to each one, -18, 5, and -10, which you can see is what we would get if we laid this column matrix across this and multiplied them pairwise and summed them up. We'd get equation 1. So now let's take and find the inverse of this matrix A. We can do that on the calculator or using whatever method we like, the cofactors, etc. So if I want to find x, y, and z, I just have to multiply by A inverse on both sides, keeping in mind that we need to multiply on the left. Remember, left and right multiplication will be in general very different things from each other in matrices. Now, though, we can multiply these two together to get the following, and then we decode this as our answers for x, y, and z, respectively. We'll look in the next video on some other ways that you can do the same thing, that we can assign values from a system of equations to some matrix and use matrix operations to establish the answer, if one exists, in any number of equations and the same number of unknowns. But for right now, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies, and I'll see you in the next one.